Hey guys, so I'm at a soccer tournament today. So you guys are going to be going to the computer lab today. You're going to be working on your project. Before you go though, there's a little bit of a note that we have to finish that we started on Friday, and I want you to get it done today before you do your lab tomorrow. All right, so Ben, Emily, and Marissa, I think that you were gone on Friday, so you missed the loads in series section of the note. You're going to have to copy that off someone else, and then today we're going to be working on loads in parallel, okay? So I'm just going to shrink this down. And we are going to be working off of the worksheet that you should already have in your notes. You got it on Wednesday or Thursday last week, I believe. And we did that on Wednesday or Thursday. Second part is loads in series. So we already finished that on Friday, right? That was when we did the super fun math equations on the board. That's the Ben, Emily, and Marissa. You guys are going to have to copy that down. And then loads in parallel. That's what we're going to be doing today. So if you can just turn to that part of that note. Anyone that doesn't have it, there's extra copies on the front desk. So if you want to come grab that, that'd be great. All right, so like I just mentioned, we're going to be talking about loads in parallel today. We already talked about loads in series on Friday. So first thing I want to do is I want to highlight some important information that you might need to know when we're going through and when we're solving some of these equations. So I'm going to go ahead, I'm going to pull up my, no, I don't want to set up time machine. I'm going to go ahead and I'm going to pull up my highlighter function. And I'm going to go through and I'm going to highlight some of the info that we are going to need to solve this equation. We know that resistance is 5 ohms. You can find this in the paragraph right at the very top of your sheet, all right? So two circuits are made using light bulbs with a resistance of 5 ohms. Remember, every time that you add a light bulb or load, you're adding resistance. We also know that our battery has a potential difference or a voltage of 10 volts. So we're going to need to know that too. You can highlight this, you can star this on your note, or you can just follow along. That's fine. We know that the first circuit has 1 bulb, and we know that the second has 3 bulbs, and we know that they are connected in parallel. So exactly like Friday, we're going to be looking at 2 different circuits. That just like Friday, the first one had 1 bulb, second one had 3 bulbs, except this time we're going to be looking what happens when they're connected in parallel compared to in series. So the whole point of having this, what happens to voltage, what happens to current, and what happens to resistance. All right. So next thing that we are going to want to do is we are going to want to draw these circuits. So let's switch the page here. Okay, so this is what you should see next on your screen. All right, you should see it's asking you to draw a circuit diagram for each of the circuits for circuit 1 and for circuit 2. Okay, so let me pull up my trusty pen here. Perfect. All right, so remember circuit 1 only has 1 load, 1 light bulb, right? So first thing I want to do is I want to draw my battery. Oh, it's got a really big end. Here, let's erase that little bottom part there. Much better. All right, then we want to go ahead and we're going to want 1 load. So I'm going to draw 1 light bulb here. Perfect. And it's a closed circuit, remember, right? Got really straight lines. Hopefully yours are a lot straighter than mine. My defense, I'm using a touchpad, not a mouse. Pretty good, right? So this is circuit 1, right? So we've got our battery and we've got our 1 load, right? And remember the potential difference on the battery is 10 volts. Okay, so now we want to draw circuit 2. Circuit 2 has 3 loads, right? And it's got that battery as well. Big thing is that everything is connected in parallel though. So last time we drew them connected in series on Friday. This time we're going to want to draw them connected in parallel. So we're going to have 1 load here. Don't judge my art skills, right? Remember, parallel, you have options, right? In series, they can only flow one way. In parallel, they have, in this case, 3 options, right? So we have our 3rd load. Let's close these circuits. Hopefully yours looks neater than mine. That's okay. Perfect. Awesome. Just going to pull up my pointer quickly. All right. So in this one, we've got our circuit with one load, right? One battery, one load, and the electrons always have to pass through this one load, right? Here we've got a bit of a sketchy looking parallel circuit, but it's got three loads, 1, 2, 3, right? And the electrons have a choice. They could flow through this load, they could flow through this load, or they could flow through this. We talked about Thursday about where this equation is derived from. Interesting to know, but really you just need to know how to plug the numbers into the equation. So don't panic too much if you were a little stuck on Thursday, all right? So let's take a look at this. We are looking at total resistance, right? So we know in a parallel circuit that 1 over the resistance of the second load plus 1 over the resistance of the third load, all right? We can already simplify this because circuit 1 has what? It has one load, right? So we don't have to look at R2, we don't have to look at R3 for circuit 1, we only have to look at the first resistance, right? So let's pull up my pen. There we go. So we know that 1 over RT is going to be equal to 1 over R1. What's R1 again? 5 ohms, right? So we know that 1 over RT is going to be equal to 5 ohms. If I plug 1 divided by 5 into my calculator, it is going to give me 0.2. All right? So I know that 1 over RT is equal to 0.2. I don't care what 1 over RT is equal to. I care what my total resistance is equal to. All right? So you do not have to copy this next part down. I'm going to pull up a blank page and I'm going to remind you very gently how to solve this using algebra. Okay, so for my math junkies, for those of you that are taking math right now, you probably know this. You're going to be bored to tears. For those of you that forget, I'm just going to pull up and show you how to isolate RT here. Okay, so let's get my pointer. Let's get my blank screen. Perfect. Let's get my pen back. All right, so where we left off, now I have lots of room to write, right? So where we left off, we have 1 over RT is equal to 0.2. Now I have to isolate and then solve for RT, right? So first thing I want to do is I want to get it out of the bottom here. How do I get it out of the bottom? I'm going to multiply, right? If I do 1 divided by RT times RT, it's going to cancel each other out, right? That's going to cancel this out on this side. But what I do to one side, I have to do the other. So then I'm going to have to times this side by RT. So I am left with 1 is equal to 0.2 times RT. Am I done? No, right? I want to isolate RT. So what I have to do, I have to get rid of this 0.2 here, right? So I divide, it's going to cancel this out, right? But what I do to one side, I have to do to the other side. So I'm going to have to divide this side by 0.2. That looks really messy, so let's rewrite this, right? So we have RT, resistance total, is equal to 1 divided by 0.2. Can I solve for that? Yeah, I only have one variable, right, RT. Then I have two numbers, can plug that into my calculator easy, right? So let's pull up our resistance page again. Quick segue, sorry guys. All right, back to the note. So we just figured out that RT is going to be equal to 1 divided by 0.2. Can I solve for that? Yes, I can. If you plug 1 divided by 0.2 into a calculator right now, it is going to spit out the number 5. So I know that the total resistance in circuit 1 is going to be 5 ohms, right? How many loads do I have? I have 1, 2, 3 loads, right? So I have to use this full equation in this case, right? So we know that we have 1 over RT is going to be equal to, what's the resistance of my first load? 5. So 1 over 5 plus 1 over 5 plus 1 over 5, right? Luckily, I've already figured out what 1 over 5 is in my calculator, so I can pretty much reduce this to a decimal right away, right? So I know that RT is going to be equal to 0.2 plus 0.2 plus 0.2, which is going to be equal to 0.6, right? So 1 over RT is going to be equal to 0.6. Am I done yet? No, I don't care what 1 over RT is. I care what resistance total is. We're going to use the same principles that we used over on this side. I'm not going to pull up that second screen this time. Okay, so RT is equal to 1 divided by 0.6. I'm going to do some fast math in my head. Not going to pit me. 1.67. Alright, so I know that in circuit 1, my total resistance, 5 ohms. And in circuit 2, when I added the loads, my total resistance, good. Coming up next is going to be current. Alright, so next up we have current, right? So if we remember from Thursday, I had that wonderful computer simulation, and we should remember, hopefully, that in parallel circuits, current splits between each branch, right? So we have this wonderful equation here. We know the current, remember I is current, right? The current at each load should be equal to the current from your source divided by the number of loads, right? So in this case, in circuit 1, how many loads do I have? I have 1, right? So the current at each load should just be equal to the current from the source, right? This case, in circuit 2, I have how many? I have 3 loads, right? So we know that the current at each load should be equal to the current from the source divided by 3, because I have 3 loads, right? So that current from the source gets split evenly between the 3 loads. Okay, so if you don't have that top equation copied down, do that now. And then this bottom part, what the heck is this? If you look at the top of your sheet, I never gave you what current was, right? I'm trying to make you think a little bit. So I never blatantly said current is equal to. What 2 pieces of information did I give you? I gave you voltage and I gave you resistance. Can you figure out current from voltage and resistance? Yes, you can, right? So our current is going to be equal to voltage divided by resistance. So that's what we're going to want to do first, right? So circuit 1, we know that our current is going to be equal to, our voltage was 10. Our resistance, we just calculated resistance. Oh, nope, go away. We just calculated resistance, and we found out that the resistance was 5 ohms, right? So we know that our current from our source in circuit 1 is going to be equal to 2. Okay, I'm going to stop us there for a second. I'm going to jump over here and figure out this current. All right, it's going to be a little bit different. Our voltage is still going to be 10. But our resistance in this parallel circuit isn't 5. We just found out it's 1.67. If you plug that into a calculator, if you can do some great math in your head, you're going to find out that 10 divided by 1.67 is going to be 5999999. We're just going to call it 6, okay? So in this case, our current is going to be 6 amps. Here, current's going to be 2 amps. Why? What's the difference? Difference is resistance, right? So here, higher resistance, here, lower resistance, results in a bigger current in circuit 2 than in circuit 1, right? But remember, we have to consider the number of loads now. So in this case, our current at each load is going to be equal to the current from the source, which is 2, divided by the number of loads, which is 1. Easy numbers, right? That's going to give us 2 amps. So we know that the current at any given load at any given time is 2 amps. Let's jump over here. Okay, so the current at any given load over here is going to be equal to the current from the source, which is 6, divided by the number of loads. How many light bulbs do I have? I have 3. So our current at any given load is 2 amps. Coincidence, right? So let's recap, right? We know that the current is split between the number of loads. In this case, our current at any given load is 2 amps. In this case, our current at any given load is 2 amps. All right, coming up next, we have voltage. All right, so now we're going to take a look at voltage. All right, so we looked at resistance. We found out that in circuit 1, the resistance is going to be 5 at any given load, whereas in circuit 2, the resistance is going to be 1.67 at any given load. Then we looked at current. We found out that current is going to be equal to 2 amps at any given load for both circuits, right? Now we're going to look at voltage. So if you remember on Thursday from our computer simulation, we know that current was split equally between the loads, right? You should also remember that voltage is equal no matter what. So in a parallel circuit, voltage is equal no matter what. So this should be an easy one, right? So do we know what the voltage of the source is? Yeah, I gave it to you at the beginning, right? So voltage of the source is equal to 10 volts. So V equals 10 volts. Over here, did I give you the source? Yes, I did. I said that V is equal to 10 volts. Are we done? Yes, we are. So voltage stays the same in a parallel circuit. So for circuit 1, voltage is voltage is 10 volts, and for circuit 2, voltage is also 10 volts. All right, so let's look at some overall conclusions. All right, guys, so we're going to look at making some general conclusions now. All right, so we've already done the math part, right? We've used the formulas that we learned on Thursday, plug them in, right? And now we're going to take a look at the numbers that we found and make some general conclusions. So looking at when loads are added in parallel, the resistance, let's think about it. When we had one load, our resistance was 5 ohms, right? When we had 3 ohms, our resistance was 1.67 ohms. So as we add loads, our resistance decreases. So that's going to be our statement we're going to put up here. So we know that in parallel circuits, resistance decreases as we add loads. Okay. Now let's take a look at current. Current was 2 amps for circuit 1 at each individual load, and current was also 2 amps at each individual load for circuit 2 as well too. So we know that current splits between branches. So current splits between branches. We also know that current stays the same at each load. So even though the current is splitting between each individual branch, the actual current itself, the amperes, is the same at each load. All right, and last thing we need to do is look at voltage. And in a parallel circuit, the voltage stays the same as the source. That one's an easy one. So these are your general conclusions for parallel. So now we've drawn general conclusions for series and for parallel circuits. All right, guys, so I just want to take a second to talk about things that you're going to need to know from the test from this, all right? So in general conclusions like this: the resistance decreases as we add loads in a parallel circuit. The current splits between branches in a parallel circuit. The voltage stays the same as the source in a parallel circuit. Things like this, statements like this, things you'll need to know for your test, same as series circuits, all right? Any of the calculations, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, things we don't need to know for the test, okay? So general conclusions, yes, you need to know for your test. The point of that before all of our current, our voltage, and our resistance calculation, in terms of parallel and series circuits, you still need to know your triangles, but these calculations from the note today and the calculations from the note on Friday, at the end of Friday, were just meant to help you understand your lab 1. You're going to be looking at current and you're going to be looking at voltage and you're going to be looking at building series and parallel circuits. So you're going to get a lab handout in a second. Make sure you read through all your procedures because it'll likely take the whole period tomorrow to do your lab. All right, so make sure you're doing that. You also need to be doing your test review as well too. So your test review is handed out on Friday. If you didn't get it, make sure that you grab one today, all right? Wednesday, you're going to have half the period to ask me questions. The other half is going to be a Jeopardy style review, and 3 questions from the Jeopardy style review will be on your test as well too, all right? Other than that, you're going to be going to the computer lab, working on your electricity project. You're going to be talking about one renewable and one non-renewable source of energy. You can work in partners. Remember, use partners with caution though too. You might end up with different marks. And I expect us to be working this whole period. This is your last chance to work on this project. And the project is going to be the Tuesday after the break. So the board's on the date already. The date's on the board already if you guys want to have a chance. All right. So working hard. I don't want to hear any bad reports. And I'll see you guys tomorrow. All right.